Would you guys rather have your exam one this Friday, or would you rather have it on Monday? Raise your hand if you want it this Friday. Well, actually, let me stop that. The reason why I put it for this Friday is because I know that some people make plans to go out of town early for the Christmas holidays and all of that kind of jazz. So there was a possibility of students, having a ski trip or some such nonsense already on the books that would prevent them from being in class on Monday. So that is why I put it for Friday. Do you have an issue similar to that?
No, I have a question.
Yes.
If it's on Monday, will there be more content on it or what?
No. So if it would start talking about parallel RLC circuits this Friday, and that material is still the first bit of material for exam 2. So there would be no new material on the test. We would just effectively swap when I'm covering parallel RLC circuits and when the exam is.
For the take-home portion, is it due that night, or how long do we have to do it?
Over the break.
Oh.
So I usually give you guys a week. So it would be due so let's say that I assigned it on, let's say that we had the exam on a Monday. It would be due the next Monday that we have class. So January 6th or something ridiculous like that. Yeah. Which realistically, the in-class or the take-home portion of the test doesn't even take 2 hours. I know you guys have stuff going on, so I give you plenty of time to do it to counterbalance all of your other stuff that you've got going on. So, all right. So now that I've prefaced that, when would you prefer your exam to be?
Monday. Right.
Is anybody violently opposed to Monday? I guess violently opposed is the wrong thing. Christine, I saw you shaking your head. What? You would prefer Monday? Okay. Anybody, like I said, anybody going to be pissed off if we push the test back at one class meeting? Nobody's willing to admit it in front of their peers, so you've all been bullied into submission. The test is on Monday. All right.
For the class Friday, would the homework also be due over the break, or after the break?
Yes. So for the homework assignment that will be covering parallel RLC circuits, it will not be due until after the break. Yeah, that's correct. Hold on, I gotta get this. So don't worry about that. I'm having some technical difficulties. Minimize that. Discard.
Practice exam is like
All right. So what I have on the itinerary for today is literally a review of what people who took me for Circuits 1 got for our second op-amp lecture. So for you guys, actually pay attention this time because we're going to use it. But for those of you that didn't have me for Circuits 1, this may be new. So we're going to be talking about commonly used negative feedback op-amp circuits. And these are kind of the building blocks of how we use op-amps for negative feedback op-amp circuits to perform what's called analog signal processing. Or analog signal processing really just means manipulating signals to make them do what we want them to do. So that might be adding them together, taking the difference of them, scaling them, attenuating them, things like that. So the first circuit that we are going to look at is what's called the non-inverting amplifier. So in a non-inverting amplifier, we very generically, and I'm going to put the resistors that are important in black and other resistors that aren't necessarily there to trip you up, but from a circuit analysis standpoint, they don't really do anything. I'll put those in a different color, and we might talk a little bit about why they're used in practical op-amp circuits, but why they don't influence behavior in our analysis. So I'm going to start with my op-amp here. I'm going to choose to put the, let's put the inverting input on top, like so. If I forget to explicitly put VCC plus and VCC minus on any of these diagrams, assume it's there. So assume the op amps are always powered such that they work the way that we want them to. All right, so first resistor that's important is going to be our feedback resistor. I'm going to call this guy R2. So hopefully we all can see just by inspection that this op amp has negative feedback. Another resistor that is important is this guy, which I'm going to call R1. We are going to ground this terminal out. I'm going to do this resistor in blue because it's not particularly important. I'm just going to call it R plus for the sake of argument. It's literally not going to show up anywhere in any of our equations. This is our input voltage. Another one that's not particularly important from an analysis perspective is this guy here. This is going to be our load resistance, RL. And our output voltage, V out, is going to be the drop across our load resistance. But it also happens to be the voltage at the output node of the op amp as well. So this nodal voltage V out here is measured with respect to ground. This V out here is defined as the voltage drop across the load resistor. Positive polarity at the output terminal of the op amp, negative polarity at ground. So these literally mean the exact same thing. Okay. All right, so we are going to be using the ideal op amp rules in order to analyze these circuits and develop relationships and all that kind of stuff. Okay. So first ideal op amp rule is that no current can flow into or out of the input terminals, meaning both of these currents are zero. Now we are going to find the voltage present at the non-inverting input node. So that's this voltage V plus. And by inspection, it will be Vn. Since no current flows through that resistor designated as R superscript plus, there is no voltage drop across it. And so all of the input voltage gets applied directly to the non-inverting input pin of the op amp. So that may cause you guys to ask the question, well, why is R plus even there? So R plus is there in a practical op amp circuit in order to limit what's called the input bias currents. So there can be currents that are flowing in the op amp under a zero state condition due to manufacturing error. This is just used to kind of get rid of that current so that it's not impacting anything down the road. So from an analysis perspective, it does absolutely nothing. From a practical perspective, this is just getting rid of bias currents. Okay. Continuing on with our second op amp rule. Since there can be no potential difference between the input terminals of the op amp, the voltage present at the inverting input terminal must also be, change back. VN. I'm gonna need to restart this program or this error is gonna keep popping up over and over again, and it's gonna drive me bananas. Save. Close that out. Open our file back up. There we go. Sorry about that. Now I'm going to apply Kirchhoff's current law at the non-inverting input node. So that's adding this current and this current together. And so what we will have is Vn divided by R1 plus Vn minus V out divided by R2 is equal to 0. I can then move V out over R2 to the right-hand side of the equal sign and then multiply through by R2 to get the relationship. V out will be equal to 1 plus R2 over R1 times our input voltage Vn. Our closed loop gain, AVCL, will be the ratio of V out to Vn, which in this case just becomes 1 plus R2 over R1. So this particular amplifier is used to boost the level of the input signal. And I can say that definitively because we can easily see that regardless of what our resistor ratio here is, R2 over R1, the minimum value of our closed loop voltage gain is always going to be at least 1, okay? Since we're using real resistors here, R1 and R2 can never be negative. So our output voltage is always at least as large as our input voltage is. Usually it is larger as long as R2 is, so if R2 is much smaller than R1, this will be approximately 0. For R2 comparable to R1, this quantity is going to be greater than 1, right? So this is how we make signals larger using an op-amp. There is a very special case of this circuit called a unity gain buffer. In a unity gain buffer, R2 is a wire and R1 is an open circuit. Okay, so in that case, the ratio of R2 over R1 literally is just 0. And so we just effectively tie a wire from this node to this node. So why would we want an amplifier with a gain of exactly 1? Yes, Isaiah.
Why would it not be R1 over R2?
Okay, so I moved V out over R2 to this side. Okay. Then I multiplied through by R2. So I have R2 over R1 times Vn plus R2 over R2 times Vn. R2 over R2 looks like 1. R2 over R1 looks like this guy here. Right. Yeah. So back to my previous question. Why might we want a unity gain buffer? Why would that be used?
You can pull however much current you need.
Exactly right. So sometimes we're going to be asked to amplify signals from transducers that aren't capable of developing a lot of current, right? So for those of you that go into, well, all of you I think are electrical engineers right now, but some of you might do senior design projects where you work with, say, biomedical engineering students or something like that, trying to help them set things up. And let's say that you're trying to measure brain waves or something like that. The transducer that measures things typically create large amounts of current. So exactly what Toby said, if you use a unity gain buffer, that's making sure that all of the current that's needed comes from the op-amp power supplies and not from the source itself. Unity gain buffers are a very important stage in practically any instrumentation amplifier used to measure real world signals. Okay, so if you're measuring things, unity gain buffers are usually your first stage. Very, very good answer. All right. Any questions about the non-inverting amplifier here? Yes, Kara.
Can you repeat what you came up with today?
So a unity gain buffer is when R2 is 0 and R1 is infinity. So effectively, this resistor is a wire, this resistor is an open circuit. Okay? Unity gain buffers are used when we're trying to measure signals. And we want the current to come from the op-amp's power supply as opposed to the sensor that's generating our input signal.
Thank you.
Mm-hmm. Yes, Katie.
How did you know your closed loop gain was V out over V in?
That's how it's defined. Okay, so that's literally the definition of the closed loop gain, is the output voltage divided by the input voltage for a closed loop system. We have a closed loop because we have negative feedback. So that is very, very different from the operational amplifier's internal open loop voltage gain. In fact, that's a great question. The open loop voltage gain of an op amp, we saw from the data sheet that we looked at on, I think, the second day of class, that it's typically for the MUA 741 op amp, was typically in the ballpark of 100,000 volts per volt. Well, I think it was listed as 100 volts per millivolt or something like that, right? That's the typical value, but that's not an exact value. That's the average value over their entire production run. So realistically, we could see that value change from maybe 20,000 to 50,000 all the way up to maybe 300,000 or 400,000. And we won't know what open loop voltage gain we have with that op amp until we literally put it into a circuit or something like that. In this negative feedback configuration, the open loop voltage gain of the amplifier is completely and utterly irrelevant. As long as it's large, we get to use the ideal op amp rules. And then we can see that our closed loop voltage gain is defined only by the resistors that we use, which is a huge advantage of negative feedback. We are not relying on the open loop voltage gain of the op amp at all. We are establishing what closed loop gain we get by applying a resistor network that we have direct control over, right? Any other questions / comments regarding this, guy? Okay. So our second amplifier that we're going to look at is the inverting amplifier. And it is literally the exact same circuit, except that we are going to swap where we apply our input voltage and where we apply ground. So we put my power supply voltages here, VCC plus and VCC minus. Here's my negative feedback loop. Still going to call that resistor R2. Still going to call this resistor R1. Vn will be applied over here. I'm going to ground this node. My resistor that we may see R plus, which again does literally nothing from an analysis perspective. My load resistor, R sub L. So this is what we're trying to deliver power to. And for the most part, does not matter at all from an analysis perspective, assuming we don't ground it. Here's V out. All right. So this is the circuit that we dealt with in Friday's class meeting, right? Our input signal is applied through our feedback network on the inverting side of the amplifier. The non-inverting side of the amplifier is grounded, right? So we can observe that no current flows into either input terminal, which means that the voltage present at the non-inverting input node is 0 volts, and therefore the voltage present at the inverting input node is also 0 volts. Applying Kirchhoff's current law at the inverting input terminal, we are going to have 0 minus Vn, so that's negative Vn divided by R1, plus 0 minus V out, so minus V out divided by R2 is equal to 0. And then rearranging ever so slightly, we find that V out is equal to negative R2 divided by R1 times V in. And our closed loop voltage gain, AVCL, will be equal to V out divided by V in, or negative R2 over R1. So for this particular amplifier, we can cause amplification, meaning that our output signal can be larger than our input signal, but we can also achieve attenuation, meaning that our output signal is smaller than our input signal. And it just depends on what resistors we choose to use, right? So we have increased functionality because we don't just get amplification. The arguable drawback is that we have inversion as well, where all that inversion means is that if I apply a positive input signal, my output will be negative. If I apply a negative input signal, my output will be positive, okay? So as a general rule, any input that we apply on the inverting side of an amplifier is going to cause an output of the opposite sign. And any input that we apply on the non-inverting side of an amplifier is going to cause an output of the same sign. And we'll see that in a little bit when we talk about differencing amplifiers, when we're putting something on both sides. The inverting amplifier, like we see right here, is literally the most commonly used op-amp circuit in the world. It's used in tons and tons and tons of different things, particularly where we don't really care about the polarity of our output voltage. So audio amplifiers and all of that kind of stuff use inverting amplifiers extremely often. Guitar effects pedals use inverting amplifiers for the gain stage. And then they use other components like diodes and stuff like that to give flipping so that you get fuzz pedals and all that kind of jazz. But this guy right here is the meat and potatoes of practically all audio amplification. Any questions regarding the inverting amplifier? All right, fairly straightforward. So now let's modify the inverting amplifier to handle multiple input signals. Okay. So this is going to be the weighted, forgetting to change the color. Inverting summer. Okay. So it is, like I mentioned a moment ago, nothing more than a modified inverting amplifier. So I'm going to have, let me put my supply voltages. So here's my feedback loop. Instead of calling this R2 now, I'm just going to call it R. You'll see why in a moment. We may have some load resistance that we're paying attention to. R sub L. Let me go ahead and take care of this guy as well. We might have some resistance that I've been calling R plus over here to handle our bias currents. And then where things get interesting is what's going to happen over here on the network that's connected to the inverting input terminal. Okay. So instead of having a single resistor, R1, I'm going to have multiple resistors. I'm going to depict this with 3, but there really isn't a practical limit as long as the currents being drawn are small. So we could combine 10 or 20 or 50 if we wanted to, input signals if we wanted to. So this is going to be my first input signal. I'm going to call it V1, my second input signal V2, and my third input signal V3. So, yes, Walker. So fantastic question. Let me pull something up real quick. So this is a brief pause here. I don't remember what format I have it in, so let me pull it up here. I do need to upload this. Let's check here. Equation sheet, that's what I'm looking for. Open it, don't rename it. So Walker just asked whether or not you need to memorize the names and all of that kind of good stuff. The short answer to that is no. You do need to be able to identify them for your exam and everything, but it's not required for you to memorize them. So on the equation sheet, which you will be provided for exam 1, which will be 1 week from today, I believe we decided on, I'm going to give you the ideal op-amp model shown here with everything defined. So VD is the potential difference between your non-inverting input terminal and the inverting input terminal. The input resistance RN is seen between those two terminals. Here's your output resistance R out. Here's your open loop voltage gain, VOL times VD. There's where your output is defined. So practical op-amp model for anything you might have to use that for. Then I go into open loop op-amp circuit. So we have the non-inverting comparator and the inverting comparator, as well as the input-output relationships for both of those circuits. Then we have our positive feedback op-amp circuit. So the non-inverting Schmitt trigger and the inverting Schmitt trigger, as well as the equation used to calculate the upper and lower trigger limit voltages for both. The astable multivibrator circuit is not going to be in the test, so it's not showing up here. Then we get into our negative feedback op-amp circuit. So starting with the non-inverting amplifier, and its input-output relationship didn't give you the open loop, the closed loop voltage gain, because that should be pretty easy. Just divide both sides by VN and there we go. Input-output relationship for the inverting amplifier. Here we have our inverting summing amplifier, or I guess I didn't put weighted, but it's a weighted inverting summer because R1, R2, and R3 are not defined to be the same thing. We'll go over that in just a second. The differencing amplifier that we're going to talk about in a moment, and then down there will be the differentiator and the integrator. So to recap, I'm not expecting you to memorize them because I'm providing them to you, but I do expect you to be able to identify them. Yes. Did that answer your question, Walker? Okay. And I'm going to post that equation sheet on Canvas for you guys so that you can see it and get used to it or whatever here shortly. All right, so going back around to our weighted inverting summer amplifier. Yep.
The last quarter you posted
I think I posted solutions to homework. Yeah, so I posted the solutions to in-class assignments. Yeah, I did not post the solutions to homework because that would mean that everybody taking circuit 1 now could just ask you for the solution. I'm not going to post the solutions to the homeworks in this class either. But that brings me up to another distraction thing. Sorry, all over the damn place today. Let me get my keyboard out here. So I'm gonna pop on my Google Drive real quick. I want to show you guys something. As soon as my keyboard decides to be recognized. My drive, let's just do it using a touch screen. 2023 to 24. Winter. Circuits 2. Shared with students. Every single one of you has a folder with your name on it and all that kind of stuff in this folder, and it has been shared with you on your Google Drive. This is where all of your homeworks and stuff like that will be returned to you. So this provides feedback on how you did on the problem, and it should also, because I pay my graders enough money, also tell you, where you made a mistake and explain what the mistake is and all of that kind of good stuff. So it shouldn't be necessary for me to provide you with a solution, because the grader, if they're doing their job correctly, is telling you not only you made a mistake, but what that mistake is. So on your Google Drive, every single one of you should have a folder like this that's already shared with you, and this is where all of your homework and stuff, your graded homeworks and assignments will be found. Just as a heads up, because you all are electrical engineers, or at least the overwhelming majority of you are electrical engineers, you're going to have to work with me for the next 3 to 4 years. This is how I always return all homeworks. This is how you're going to get your test grades back. Literally everything will be put in a folder and shared with you, because I can't lose it if it's here. So, any other questions before we get back to actually talking about class stuff? Or actually, I do have a comment. I'm not going to open up anybody's homework or put anybody on blast. I will say specifically, though, that my grader told me that there were some students who were very obviously using MathCAD and not showing their MathCAD work. And so they got docked 15 points for that. And then also make sure that you're boxing in your final answers and all that kind of stuff. I don't know how much she counted off of that, but she said she was pissed, so stop doing it. So anyway, all right. There should be notes on that, and I believe she also, and she might get pissed off at me for this, but that'll be okay. If you didn't include your MathCAD or you didn't do that and she took points off, resubmit it with the corrections and she can regrade them and get you some points back. She graded them aggressively to let you know she wants it done correctly, which I told her to. So anyway, all right. Weighted inverting summer. After 5 minutes now, let's finally talk about this damn circuit. So we know this current is 0 amps. We know this current is 0 amps. By inspection, we can see that this voltage is 0 volts, which means the voltage at this node is also 0 volts. Now we're going to apply Kirchhoff's current law at the inverting input node. So we're going to add these 3 currents and this current flowing to the right together, set them equal to 0. So that's going to look like negative V1 over R1 minus V2 over R2 minus V3 over R3 minus V out over R is equal to 0. And rearranging, we will find that V out is equal to negative R times V1 over R1 plus V2 over R2 plus V3 over R3. We can't really define a closed loop voltage gain generally for this circuit because we have 3 input signals, but it should be fairly obvious that the gain experienced by our first input signal V1 is just going to be negative R over R1. The gain experienced by our second input signal is going to be negative R over R2, and so on and so forth, right? So this is literally nothing more than the circuit that we have up here, except now we have multiple input signals, each of them being scaled by a different factor that is determined by the ratio of this resistance R to this input resistance R1 through whatever. Okay. So this is a weighted inverting summer because each individual input signal gets weighted by its own scaling factor, right? So if R1 isn't equal to R2 isn't equal to R3, then the voltage V1 is scaled by a different factor than the voltage V2 is scaled by a different factor than the voltage V3, right? If R1, R2, and R3 were all equal to each other, this would no longer be a weighted inverting summer. It would just be an inverting summer where everything would be scaled by a factor of negative R, which is our feedback resistance, divided by whatever our input resistance is, right? I probably talked about this as an example of where an inverting summer is used, but how many of you have ever traveled across a state line and seen a weigh station? Practically everybody. The weighted inverting summer, or really the inverting summer, is how those load cells, the output of those load cells are added together to determine the weight of a truck. And it's scaled by a simple resistor ratio that converts whatever output the sensors give, be it in kilograms, pounds, or whatever, tons, into a particular weight value, right? So you can just set that scaling up by using the appropriate resistors, and then you just add the weight experienced by each load cell together to get the total weight. It's also how your bathroom scales, your digital bathroom scales, and all that kind of good stuff work. Yes, Ethan.
Can there be more than three, like it could be?
Oh, absolutely. So the only real constraint is the total amount of current that's going to wind up leaving the output node of our op amp, because that is limited. So a real op amp can't handle like 40 amps of current or something like that. So we could put 10 here as long as the total amount of current was an allowable amount for the op amp to handle. We're good. Yes.
Those resistors have to be higher than RN, RL.
So we don't want them higher than RN ever. So if they were higher than the internal input resistance, this current would no longer be zero. So these resistors right here typically need to be significantly smaller than the input resistance so that no current branches off and flows here. This load resistance needs to be larger than the internal output resistance, or we'll see that effectively the voltage divider in our practical op amp model causes too large of a voltage drop over the internal output resistance. So usually the internal output resistance is on the order of tens to hundreds of ohms. So this is in kilo ohm scale in order to fix that part. And the internal input resistance is on the order of mega ohms. So we put this also in the kilo ohm scale to fix that. So that's why kilo ohm size resistors are used to bias op amps in practically every conceivable application. All right. Any other questions regarding the weighted inverting summer? Isaiah.
Said the R.
So it's not to ensure that no current is flowing through the op amp because the internal resistances. There's a quantity called input bias currents that are due to manufacturing errors in the op amp fabrication process. And this resistor is to try to cancel out some of that. We'll talk about that more when we get into our electronics classes, talking about how more of the internal workings of one of these guys works. Because from an analysis perspective, this R does nothing. Because we're not paying attention to what's happening inside of this thing. So let me ask you guys a conceptual question here. Could we make a weighted non-inverting summer? Meaning, could we set up some network connected to the non-inverting terminal and get something that looks like this? Short answer is yes, but the math gets ridiculous, okay? So let me show you what I mean by that. I'm just going to do two inputs on this side, right? This isn't something that's practically done literally ever, so you don't need to write this down. I just want to illustrate a point. So let's say that we had an op amp like so. I'm going to put the non-inverting terminal on top. So let's see. Here's my feedback resistor. I'm going to call it R sub F. Here's some resistor. Let's call it just R for the sake of argument. I ground this guy. Here's R1 and input voltage V1. Here's R2 and input voltage V2. And then over here is my output resistance, like so. So we can see pretty easily, this current is 0 amps. This current is 0 amps. This voltage V plus is going to be more difficult to figure out, right? So in order to figure it out, I'm going to literally disconnect that portion of the circuit and find a Thevenin equivalent of it. So here's my voltage V1 in series with my resistor R1. Here's my resistor R2 in series with my voltage V2. And this is my Thevenin equivalent, which is going to be the same as the voltage drop applied at this node. All I've done is just disconnect everything to the left of the inverting, the non-inverting input node. And I'm going to use that to figure out what this applied voltage would be, right? So any thoughts on how I might find that open circuit voltage? I'm going to choose to use superposition. Might not be super obvious here, but if I choose to use superposition, this is just two voltage dividers. I'm going to add their outputs together, right? So with V1 on and V2 off, VThev single prime is going to be just the voltage drop across R2. So that's going to be V1 times R2 over R1 plus R2. With V1 off and V2 on, now the output voltage is just the voltage drop across resistor R1 because it's connected between this node and ground, which is another voltage divider circuit. So VThev double prime is going to be V2 times R1 over R1 plus R2. And then adding these results together, I get V1 R2 over R1 plus R2 plus V2 R1 over R1 plus R2 is equal to V1 R2 plus V2 R1 all over R1 plus R2. So I still am going to wind up amplifying the sum of my input voltages, but they're scaled by these weird factors, right? So it's not nearly as easy to determine how the output signal is going to work. And for every subsequent branch that I put on this thing, this gets more and more difficult, because if I had a third branch, then this VThev prime would be V1 times R2 in parallel with R3 in parallel with blah, 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 divided by R1 plus R2 in parallel with all of that other stuff, right? So practically, we can do it, But from a figuring out how it's going to work, using the non-inverting amplifier, excuse me, using the inverting amplifier as our basis of modification makes all of the math work out much, much easier. If we ever wanted to make sure that our output signal from our inverting summer was positive or the same polarity as our input voltage, we would typically just add a second stage to convert that negative output voltage back into a positive output voltage. Isaiah.
How come it's the RF, the feeding back from the non-inverted side?
Do what?
How come the RF is the
Because that would be positive feedback. We had an entire class on it.
okay?
So we are dealing with negative feedback circuits. So if I put RF, connect it to the non-inverting input, I no longer have a negative feedback circuit, which means my output is either going to be the positive supply voltage or the negative supply voltage, which isn't an amplifier. And I'm trying to get actual amplification here. So, like I said, we can choose to do to put our input signals on the non-inverting side, but it winds up making the math atrocious for anything higher than 2 input signals. So realistically, this is as good as we're going to get for adding signals together in any form that makes any sense. Okay. All right. So now let's talk about our differencing amplifier. So in a differencing amplifier, we have our op amp. I'm going to put inverting input terminal on top, VCC plus, VCC minus. Here's my negative feedback. I'm going to call this resistor R. I'm going to have another resistor here, also R. A resistor here, R. A resistor here, also R. I'm going to call this voltage V1, this input voltage V2. Here's our load resistance, which doesn't particularly matter, and it's the only resistor in this circuit that doesn't particularly matter. And then here's our output. So there are a couple of different ways that we can think about this circuit, okay? So for example, if V2 were 0 volts, meaning that this input node was shorted to ground, what kind of circuit would this be? Go back in your notes from 10 minutes ago. All of them are negative feedback. An inverting amplifier, right? So with these two effectively in parallel, we would have a resistance R plus of just 1/2 R, but that really didn't do anything for how our inverting amplifier behaved, right? So with V2 turned off, this is just an inverting amplifier, and we would know that our output would be negative V1. What if V1 is turned off? What is this thing? A non-inverting amplifier, but we also have this resistor network here out front, right? So let's analyze it as a whole picture, but with the understanding of that in some way, shape, or form, this is kind of both an inverting and a non-inverting amplifier at the same time, okay? So we know this current is 0 amps. This current is 0 amps. This voltage of V plus isn't super obvious, but hopefully it's fairly straightforward to figure out. Anybody have any thoughts on what it might be? Right. So it is the voltage drop across this resistor R, but we should be able to quantify that. V2 divided by 2. Absolutely right. So this is just a voltage divider network. And because these resistors have equal value, exactly half of the voltage drop is going to occur across the second resistor. So V2 divided by 2, okay? Which means this voltage, V minus, is also V2 divided by 2. Applying Kirchhoff's current law to this node, we are going to have V2 over 2 minus V1 divided by R plus V2 over 2 minus V out divided by R is equal to 0. And so I can just multiply both sides through by a factor of R and change nothing, right? Because 0 times R is still just 0. So I can just get rid of those guys. So I have V2 over 2 plus V2 over 2 looks like V2 minus V1 is equal to V out. So this particular amplifier gives us the difference of whatever our input signals are. If all of these resistors are the same thing. If they are not the same value, then we get into the case where we have wonkiness, where one input signal is going to be weighted differently than the other input signal. So it's always going to give us the difference, but the input signals are going to be scaled by different factors, which might be good depending on whatever application we're looking for, and might be bad. I would argue that a better way to do that would be to chain an amplifier to the front of this guy that scales V1 by a specific amount, chain an amplifier that scales V2 by a specific amount, and then just take the difference of those things, as opposed to trying to figure out how these 4 resistors wind up working together to get us the answer that we want. So this is as simple as differencing can get. We can make it more difficult by making these R's have different values. All right, any questions regarding a differencing amplifier? Pretty straightforward. All right, so we've talked about amplification, attenuation, addition and subtraction. We can't do multiplication or division with a single op-amp stage. So now let's talk about calculus with op-amps, particularly differentiation and integration. So I am going to choose to represent these circuits using a capacitor in my circuit, but you could also make them using an inductor. And as a case in point, in your homework assignment, I ask you effectively to derive the relationships using inductors. Okay. So because we're going to use a capacitor, we need to make sure that we remember how capacitors behave. Recall that the current flowing through a capacitor, IC as a function of time, is equal to C times the derivative of the capacitor voltage with respect to time. Or alternatively, we could say that V is equal to 1 over C times the integral of our current and I'm going to choose to integrate from negative infinity to t, just so that I don't have to pay attention to initial conditions, right? We know that this integral can be written as the integral from some point in time where the voltage drop across the capacitor is known to some later point in time plus an initial condition. That's just going to make the math harder, so I don't want to do that. So these are our two relationships. I can literally never remember which one of these is which, so we're going to find out together if this is an integrator or a differentiator. But effectively, all we have is an inverting amplifier. But we're going to have a capacitor in the position of one of our resistors. So let's start by putting the capacitor here. So here's C. I'm going to put my resistance up here. Could be driving some load resistance. I may have some resistance here as well. So this will be R plus, RL. This is our output voltage as a function of time. And this is our input voltage as a function of time. All of the other circuits can definitely be used for AC signals as well. In fact, they're way more interesting if you use them for AC signals than for DC signals. But for this side specifically, we don't want a DC signal because that capacitor is going to look like an open circuit and we're not going to get anything out of it. All right. So before we get into our analysis here, I'm going to choose to represent my capacitor voltage as positive polarity on left, and I'm going to choose to represent my capacitor current. My stylus will write as flowing into the positive polarity terminal. So we can see that no current flows into either input terminal since we're dealing with an ideal op amp. The voltage present at our non-inverting input terminal is 0, which means the voltage present at our inverting input terminal must also be 0. And so now I'm going to apply Kirchhoff's current law by adding this current together. Yeah, I can do it that way. We'll just add an extra simple step. Adding these two currents together that are leaving our inverting input node as we've done previously. And so what I wind up getting is negative IC minus V out over R is equal to 0. And I can rearrange this slightly to find that positive IC is equal to negative V out over R. We'll play around with that more in a minute. So your murmurings, anything not straightforward here, using the exact same approach I've used in every other circuit. Apply ideal op amp rule number 1 to show that no current is flowing into either input terminal. Apply ideal op amp rule number 2 and solve for V plus. Apply the same voltage here at the inverting input terminal, and then apply Kirchhoff's current law at the inverting input terminal to get a relationship that tells us what's going on with V out. Literally the exact same process for every circuit I've worked in. Okay. So our goal for this thing is to figure out how V in and V out are related. And so I'd be willing to bet that it's got something to do with this current IC. Okay. So IC is related to C times the derivative of our capacitor voltage. So we could substitute that in. So C times the derivative of our capacitor voltage with respect to time will be equal to negative V out divided by R. Now we need to figure out what the relationship between our capacitor voltage and our input voltage is. Anybody care to venture a guess? Or hopefully more than a guess? Hopefully you know what it is. VN. Why is it just VN? Right. So this node right here represents the positive polarity terminal of our input voltage Vn, and it is also the positive polarity terminal of our capacitor voltage Vc. The negative polarity terminal of our input voltage is assumed to be at ground. Well, the negative polarity terminal of Vc is at ground effectively. So Vn is exactly equal to Vc. So we have C times dVn divided by dt is equal to negative V out divided by R, and then rearrange this ever so slightly, and we find that V out is equal to negative R times C times the derivative of our input voltage. So this is a differentiating amplifier where the output signal is a scaled version of the derivative of the input signal. This particular circuit is used very often in both control systems and communication systems. In a communication system, it's used as, if I'm remembering correctly, a low pass filter. We'll figure that out in about a month, but anyway. It's used as filters. It's also a large part of what's called a PID controller, so a proportional integral differential controller. This is the D stage, right? Providing differentiation. So you're going to see this in several classes. Later on in this class, circuits 3, and then linear systems and signals, and then controls and communication classes later on. So this is a fundamental building block of a lot of different electrical engineering applications. If we want to make an integrator, what time is this class end? 1:45. All right, we got to do this relatively quickly. If we want to make an integrating amplifier, we simply swap the position of our feedback resistor and our capacitor. So we'll put our capacitor up here and our resistor down here. All right, so try to run through this fairly quickly. That's going to be R, that's going to be C. Resistor that doesn't really do anything from an analysis point. R plus, load resistance. Let's define our capacitor voltage like so. And our capacitor current like so. So now we can say this current is 0 amps. This current is 0 amps. This voltage is 0 volts. This voltage is 0 volts. That 0 looks too much like a 6 for me. Adding these currents together, we wind up getting negative Vn minus, plus, dang it, that's not right. Negative Vn over R. There we go. Plus IC is equal to 0, which we can rearrange as Vn over R is equal to IC. So in some way, shape, or form, our capacitor current IC of T has to be related to our output voltage. We know that the capacitor current is related to the capacitor voltage by that integral-based relationship. So let me scroll up here so I can remind myself of what it is. Boop, 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 boop. Boop, 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 boop. Sorry, I'm just having a brain fart here. The negative Vn over R is equal to IC. That's true all day. IC is equal to the derivative. Yeah, okay, we'll go about it in a slightly different way. All right, so what's the relationship between VC and Vout? So Vout is negative VC. So if this is the positive polarity terminal of Vout, it's at the same node as the negative polarity terminal of VC. This is the positive polarity terminal of VC, and it's at ground. This is the negative polarity terminal of Vout. So Vout is equal to negative VC. Negative VC is negative 1 over C times the integral of IC and now we can substitute in our relationship for IC, noting that R is a constant, and we get negative 1 over RC times the integral from negative infinity to T of Vn of T prime dt prime. So there is our relationship. Now, realistically, we don't really know what the input voltage is doing at negative infinity or anything like that. Excuse me. So in a practical circuit, we would actually just put a resistor in parallel with a capacitor C that's going to ensure that any energy initially stored in this capacitor has a way to get to ground or be dissipated. But it makes the math harder, so I didn't put it in. All right. So that is enough out of me for today. Yes.
What is T prime?
So T prime is just a dummy variable for time. So because I have T in the limits of my integration, I can't have T down here as well. It'll be too confusing. That's it.
Okay.
So this is time, this is also time, but I can't use the same symbol because it appears in both places. And when I perform that integral, it's just going to look odd. So if it makes you feel better, call this X. Anything representing time.
That's just a different.
Yes. All right. Thank you guys for your time. And I will see you on Wednesday where we're going to talk about cascaded op-amp circuits. And that'll be our last topic for the test.